Ladies and gentlemen, and my name is Meng from 3D R&D Center. It's my great honor to have this opportunity to share the report with your audience. Here's my self-introduction. And I'm working at the 3D R&D Center and thriving on to solve the users' various problems. And SuperMap 3D GIS has gone through more than 10 years of development. Let's make a quick retrospect what we have done over the years. In 2005, Google released the first virtual Earth product, which triggered a huge wave of 3D GIS applications. In 2007 to 2008, SuperMap also began to develop our own 3D products. And in 2009, we proposed the 2D and 3D integration technology and released the first 2D and 3D integrated GIS platform software at that year. In 2014, with the widespread application of oblique photogrammetry technology, we supported the oblique photography data and make good use of it. Moreover, SuperMap provides GPU-based 3D spatial analysis, and it is now the standard with every GIS platform. In 2015, one of the partners applied SuperMap 3D GIS to the beam industry, the Shanghai Tower and the Yangjiang Hydro Power Station project have applied SuperMap Beam plus GIS technology in their operation and maintenance system. 2016, the first year of VR, we started to support VR helmets. We launched a new client product based on the WebGL technology, and this product has become the mainstream now. And most of our users have upgraded from the plug-in product to the WebGL product. And we will further the in-depth development of 3D GIS and make better product as a service to the overseas users. After years of R&D, we come to the conclusion that the development of 3D GIS is driven by the following factors. The first one is the cutting-edge information technologies, such as WebGL, XR, and 3D printings. The second one is data, such as oblique photography data, point clouds, and the beam, which reduce the cost of data acquisitions. The third one is the market. The GIS applications in China are very widespread platform. The fourth one lies in the product level. The widely use of smartphones accelerated the development of mobile GIS. WebGL makes zero client possible, and cross-platform application requires Linux 3D functions. On 2D and 3D integration, new 3D GIS technology has played the vital role in the technical innovations. During years of development, we have gradually formed a new generation of 3D technology system. The cornerstone of the entire technical system is the data model. The presentation of the real world, spatial analysis, integration of multi-source data are based on those data models. I will introduce these models and the thinking behind them in detail later. 2D and 3D integrated GIS technology includes integration on data storage, analysis, and software. In terms of multi-source data, except for the traditional GIS data, we also support more special data such as oblique photography data, beam, point clouds, terrain, and pipelines, and so on. And last year, we started to use distributed technologies to enhance the full process management of 3D data. Special 3D model data format is published last year, and it is the first group standard about 3D GIS data in China. Also, we have the Open Geospatial Database Connectivity. We call this OGDC, which is a national data access standard we have introduced a few years ago. Through these two standards, we hope to promote an open GIS community. As for 3D data interaction techniques, we have used WebGL, VR, and AR in SuperMap products. I will introduce in detail the new generation of 3D technology system and its applications. First of all, the new technology for 3D interaction and output. AR brings us more immersive, interactive experience than ever before. Let's check out this video. Based on AR, we can place a virtual beam model on a real desk. It's the SuperMap Chengdu headquarters. A lot of GIS analysis and query functions could be integrated with AR to achieve the combination of the virtual space and the real world. Now, SuperMap AR 3D app is widely applied in many pipeline and beam projects. Except for AR, we have another very important technology in 3D interaction, the WebGL. So I'm going to highlight this. Let me focus on the three aspects. The first one is the high realistic 3D scenes. Many users do care about the cool effects shown on the game engine, so the WebGL can do the same thing again. We added a lot of special effects last year, such as custom light source, dynamic texture, plus self-illuminations, and scanline effects, and bloom effect, PBR rendering, and OIT rendering for the more vivid effects. We can also create more effects using Unity 3D, the game engine, then exported these effects to SuperMap. In this way, we can migrate, or let's say, upgrade CS applications to BS architecture. SuperMap users has applied these effects to many industries. Now, it is part of the Intelligent Operation Center solutions. In WebGL, we provide particle systems and various particle types, such as the fire, the fountain, and the rings. And we have made a lot of optimizations to ensure that the particle system renders smoothly on the WebGL. This is a typical example about an emergency project made by one of our clients. As you see in this video, its performance and functions can be completely covered by the SuperMap Icon 3D for WebGL product, so that many effects can be done by the plugin products before can be migrated to the WebGL product now. The second feature is the rich data representations. As we mentioned before, WebGL now is capable of full data support, and all types of special data can be displayed and used on it. More than the static data, but also the streaming data. In this video, by receiving streaming data, each wind turbine fan rotates at its own speed, and SuperMap using dynamic layer to improve the performance, which support running over thousands of dynamic objects at the same time. SuperMap WebGL product uses instance layer to effectively represent massive symbolic objects. We can create plants, forests, grasses, and render them with high performance. For point cloud data, we introduce EDL rendering mode because it's difficult to recognize each feature under the normal render mode. And under the EDL mode, it obviously improves depth perception, thereby to achieve more interactive rendering. The MBT tile has been used widely in GIS these years. SuperMap iClone 3D for WebGL could parse, load, and display massive vector tiles on the fly. And we can do the selection, querying, and color settings are supported too. Now, SuperMap WebGL product could run over 100 million of vector data. In terms of beam, sectioning is an important feature, especially the need for the indoor applications. In response to this demand, we also provide various sectioning functions such as cross, vertical, and horizontals. We also provide a splitting feature for the over and underground scenes. This can be very convenient when browse a building and underground pipeline at the same time. The third one is performance. This is a 500 square kilometer fine model, which is very good in terms of loading performance. Same as the point cloud, over 300 gigabytes, and it goes smoothly. So far, I have introduced new technologies for interaction and output. Next, I will address SuperMap 3D data model system for the full-time representation. As we all know, the soul of GIS is the spatial analysis. The fundamental element of spatial analysis lies in the spatial data model. The first one is the object models. In 2D GIS, we use point, lines, and polygons to represent abstract objects. Thin grid to represent terrain and imaginary, but it's only 2.5 dimensional data. In 3D GIS, we are going to exhibit the real world with the 3D solid data. And finally, also use 3D printing to restore the real world. SuperMap uses high precision, topologically closed meshes to represent the 3D solid data. And then we can perform many practical functions, such as Boolean operations, spatial relations, and calculation of volume and area, and 3D printings. Object model now is well used to present many kinds of data. For example, the CDGML is a data model and exchange format of 3D models for cities and landscapes. And we can directly import this data into SuperMap, including its materials, textures, LOD, and attributes, and export the model to CDGML files. Let's look at another 3D solid data, the beam. We can import beam models into SuperMap platform and use as the 3D solid data model to represent the beam. One advantage is that the SuperMap can get the section plane from the beam. Also, a 3D solid model can also represent geological bodies. Each geological layer can be seen as a 3D solid model. We can slice or cut the geological body by spatial operations. Let's check out this application. It's a case which one of our clients use SuperMap 3D platform on the metro line constructions. As you can see in this video, we virtualize the position of each shield ring and its surrounding cascades and measure the distance among them. By the real-time analysis and calculations, we can effectively forecast the potential risks and make practical plans to improve construction effectiveness and safety. 3D solid model can also represent the terrain and the geomorphologic data, and export the terrain to the STL format, then for 3D printings. Besides that, the 3D solid data represent not only the physical objects, but also the professional abstract models. This is one of the projects with our close telecom partner. they use 3D solid data model to represent the professional model, the antenna lobe. 3D solid models can also be used to represent the models of the spatial analysis. For example, in the real world, the range covered by the shadow is a plane, but in 3D space, it can create a shadow body. Users will get analysis results as solid geometry, so they could use it for further calculations and or analysis. As for urban planning and zoning, in real world, zoning regulations are relevant to everyone's life. We may use this to promote public welfare and avoid conflicts in our districts or neighborhoods, because the regulations or ordinance cover considerably large number of details. Use manual zoning examination in practice is quite laborious. With the help of 2D and 3D data models and spatial calculation and analysis, we could translate the regulation text into digital rules and implement auto examinations in virtual space and solve the problems for the real world. Now we have a lot of automatic examinations, such as the building heights, setbacks, and the sunshine, and others. It's now much less consuming than ever before. Here's a demo of the building heights. The user could calculate the precisely height instead of interactive measuring. With the wheel zoom analysis, we can see this visibility from a given point in a 360 degree of view. From the result, we could know that the 83% of the aerial space was obstructed by the skyscrapers, so people may feel depressed under that circumstance. Vertical clearance is the minimum vertical distance on the overhead structures, and insufficient vertical clearance in extreme situations can result in closure of the bridge for a long time. In SuperMap, use given XY coordinates, we can calculate the minimum vertical distance from the bridge or other models to make these rules make the rules examined by automations. This is another project. Our user use digitalized rules to achieve automatic examinations for over and underground circumstances, such as general zoning, building heights, and basement heights. The second data model is the field model. Tint and grade are commonly used to display 3D data, such as the terrain, and how to represent continuous and heterogeneous data in 3D space. When we countered with haze and smoke was severe in the past few years, some users put forward a demand that how to analyze the distribution of the pollution in 3D GIS, and how could we represent the coverage of 5G signals. Therefore, SuperMap has upgraded TIN to TIM to meet such a demand. TIN is built from Delaunay's irregular triangle network, and 3D Delaunay algorithm can also generate the tetrahedral irregular meshes, and then discrete 3D points into continuous space, so as to represent the true distribution of the field data in the physical space. Moreover, we promote the grid to the voxel grid. In 2D GIS, grid can only represent two and a half dimensional space. Voxel grid enabled to represent the true real 3D space. For example, the voxel grid can be used to represent the duration of the sunlight distributions. In this case, for 5G signals represented as voxel grid, are attached to the surface of the model, indicating the current signal coverage. And with the help of the voxel grid model, user could adjust the position of base stations to optimize networking. Air pollution in certain area can be represented using voxel grid tool. We can see the distribution of the pollution conditions by dynamic filtering. Another example is a project from National Earthquake Center. And we use seismic velocity sampling data and interpolate them into voxel grids and then generate I3M tiles. It will help experts for better monitoring the outliners and understanding the underground structures. In this way, we have built a data model system for the full space representations. Next, I will introduce multi-source data integration and distributed processing technologies. We have supported a variety of 3D data at early days. And let's take a look at BEAM again. BEAM manages integrations empower users to introduce geographic context to assess the environmental impact, analyze multi-source data, and improve communication with stakeholders. For the integrations, the most important step is to efficiently import the models that are made in BEAM software into GIS platform. Now, SuperMap has supported to import data from various BEAM modeling softwares, listed in the left side. Once the BEAM model is imported into the SuperMap platform as 3D solid data models, then we could do some works in depth, such as the spatial analysis and the query on these models. And how to integrate BEAM models with another data types. Here is the project from Yalong River. We can see the winds in the picture were designed by the Dassault's 3D experience. As we all know, DM and BEAM come from different software with different way of modeling. So how it comes to precisely put this BEAM model into the terrain, that is a big challenge to us. First, we could use the coordinate translations to place all kinds of 3D data under one certain coordinates, such as the WGS84. The second step, we use spatial operations to deal with the overlapping part of DM and BEAM. After that, the two types of data are matched precisely, whether we look from afar or close. Here are another cases. Now we can combine BEAM model and another data in a large scale to meet the needs of applications. When BEAM upgrades to SIM, let's call the city information modeling, GIS still play a key role for the applications. We provide a unified coordinate system and 2D and 3D base maps, and GIS could manage the network of links between different BEAM components and special analysis and queries. Finally, SuperMap provides multi-end support, including PC, mobile devices, and web use. Within the further development of BEAM applications, Dassault and SuperMap reached the global strategic partnership in June last year, promotes global implementation and innovation of BEAM plus GIS. And later, Mr. Kevin Zhu from Dassault System will cover this topic later. This is a traffic program focused on the construction stage, cooperate with Dassault Systems. Using SuperMap platform as the operation and maintenance management applications platform. Another source data people now are paying more attention to is the oblique photography data. Now we have supported the oblique photography data in 2015, generated by context capture and strict factory. We have applied oblique photography data in many industries, such as emergency, planning, and real estate management. When we came into the contact with such kind of DSM data, one of the core difficulties was how to manage each building on it. Our idea is that instead of splitting or cutting the original data, we directly add the vector polygons on it for the simulations. In this way, SuperMap extends many GIS applications towards oblique photographic data. And SuperMap can overlay the oblique photography data with streaming videos, as we can see in this picture, for better effective monitoring. After years of development and cooperation, we and the partners have built a full ecosystem of oblique photography and GIS. Last year, we built a strategy of cooperation with DNJ to promote the application of the entire industry, from drones data collections to the applications. This data is generated by the DNJ automatic modeling software and browsed on SuperMap platform with high accuracies. With the rapid development of data collections, it seems impossible to deal with massive 3D data efficiently in the traditional way. Let's check out this case. The user provided us a set of oblique data with over 500 square kilometers with 3 centimeter accuracy and over 3 gigabytes. It could be extremely slow to copy this data to one single computer, let alone to manage it. Now we use distributed technologies to process and manage this massive data. First, we have adopted distributed file system to manage the large-scale oblique data, and in order to make it more effectively, we upgrade from standalone operators to the distributed operators. Let's check out the test result. Under the standalone mode, it takes 21 hours to go through the 4 operators, merge the root nodes, singulate, and cover to the S3M, but it only takes 3 hours under the distributed processing mode. And it's more than 7 times faster. The same way we can use on the point cloud. Under the standalone mode, it takes 15 hours to build index, LOD, and convert to S3M. The test results shows 7.5 times faster than the traditional way. Our target is a full process management of massive 3D data based on the distributed technologies, from data accessing, processing, and service publishing, and use on multi terminals. The last part I'm going to share with you today is the 3D data standard and its applications. And once upon a time, one of our users has asked us, can SuperMap support the format conversion between the S3M and 3D tiles? So we open sourced our S3M data format at GitHub in September 2017. And it's attracted the attention of the GIS industry. On August 31st, 2019, the special 3D model data format was officially implemented. This standard is also the first 3D GIS domestic group standard, and 12 national organizations participate to apply for the S3M standard applications. Using S3M, we can we can support all kinds of data, and we can use this with on multi-terminals with high performance. Therefore, we have offered some free S3M tools. The first one is a toolkit for data reading and writing. It's compiled in C++. The second one is the data format for converting different file systems. The third one is S3M reading SDK for the web use. And now more software supporting S3M directly now, such as Altiger and DNJ Terra. Through an open S3M read and write SDK, this software could directly generate S3M data and publish the service and display in the browsers with ease. For other industries such as BIM and geology, this kind of data can be imported into SuperMap products through an open data accessor, the OGDC. And we also provide tools for IFC and the 3ds Max for the users to import their data. Besides S3M data format standard, we will provide the S3M service API standard in later, thereby to establish an open 3D data standard system for empowering the GIS industry. Coupled with the open 3D GIS data standard, SuperMap gradually built an open ecosystem, including the GIS platform software, oblique photography modeling software, and many application platforms. And we do hope to enable the 3D GIS ecosystem through an open 3D GIS standard system so as to promote the sustainable development of the 3D GIS industry. So here's come to the end of my section. Thank you for your listening. Thanks again.